Dear students, welcome to the 11th lecture on statistical mechanics. In the previous lecture, we studied about Fermi-Dirac distribution. We derived Fermi-Dirac distribution law. And today, we study an application of Fermi-Dirac distribution, that is free electrons in metals, electron gas. So we will study the application of Fermi-Dirac distribution in electron gas. Free electrons in metals. We know that metals are very good conductors. The high conductivity of metal is due to the presence of free electrons. These free electrons inside a metallic conductor move freely inside the metal, and in this way, these free electrons contribute to the conductivity of the metal. They continuously collide with the fixed atoms and thus behave like an electron gas. These free electrons in metal belong to most characteristic system of fermions. We know that the electron is a fermion because electrons obey Pauli's exclusion principle, and also the electrons have half integral spin angular momentum in unit of h cut or h by 2 pi. Since electrons are fermions, we shall apply Fermi-Dirac distribution to study this electron gas. Fermi-Dirac derived an expression for distribution of energies among electrons in the electron gas in a metal. Consider an electron gas having n free electrons in a metallic conductor whose volume is V. So n is the total number of free electrons and V is the volume of the conductor that we are considering. The total energy of electrons be E. E is the total energy. Practically at all temperatures, the lower level energy bands are filled with electrons. So I hope you studied the energy bands in conductors in your +2 classes. So for metals, the valence band and conduction band are overlapped. So the upper level energy bands are only partially filled with electrons. The distribution of electrons is to be considered only in the upper bands called the conduction band. So the upper band is called the conduction band and the lower energy level bands are fully filled with electrons. But the upper band, that is only partially filled with electrons. So that electrons will behave like free electrons. So here, NEDE is the number of electrons having energy between E and E plus B. So as we considered in the previous cases, we shall consider NEDE is the number of electrons having energy between E and E plus B. So the expression of NEDE can be written like this. This we obtained from Fermi-Dirac distribution law, which states that Ni is equal to Gi by e raised to alpha into e raised to Ei by kT plus 1. NEDE is for continuous, NEDE is for a system which have continuous energy distribution. So NEDE is the number of electrons having energy between E and E plus B, and this is the Fermi-Dirac distribution law for a system having continuous energy distribution. And the number of states GD can be obtained as this one, 8 root 2 pi Vm to the power of 3 by 2 by h cube into root ED. This is the expression for GED. GED can be called density of states or number of states, that is the energy states available between an energy range E and E plus D. So this expression can be derived, and the derivation of this equation is given in the appendix of lecture notes. You may refer the lecture notes for understanding the derivation of this equation. So we shall substitute the expression for GED in equation 89. So upon substitution, we will get equation 91. So this is the expression for NADE, that is the number of electrons having energy between E and E plus D. The above equation represents the distribution of energy among free electrons. So equation 91 we obtained from Fermi-Dirac distribution. So we obtained uh, the energy distribution equation for electrons in metals. Now we will study an important concept, that is Fermi energy for electron gas in metals. The Fermi energy can be obtained by filling up the energy states in the metal sample at T is equal to 0 with the n free electrons it contains in the order of increasing energy starting from E is equal to 0. So here, suppose in the metal, we are setting the temperature is equal to 0. So that is the absolute Kelvin, absolute 0 temperature, that is 0 Kelvin. So when the temperature is 0 Kelvin, we know that the energy of the electrons will be very lower. So all the electrons will tend to occupy the lowest possible energy state. But we know that the electrons are fermions, and because of that, only one electron can occupy in one energy state. So because of Pauli's exclusion principle, the electrons will be forced to occupy higher energy states because not more than one electron exists in a single energy state. So electrons will be started to filling up from the lowest energy state to upward in such a way that one electron will stay in one state. So the highest state to be filled will then have the energy E is equal to EF, and that energy is called Fermi energy. So you have to understand the concept of Fermi energy. Fermi energy is defined as EF. So at absolute 0 temperature, if we fill up the energy states from the lowest state, then the highest energy of the state which is occupied is called Fermi energy. E is equal to EF. So all the energy states less than E is equal to EF will be filled, and all the energy states higher than E is equal to EF are empty. So the definition of Fermi energy is given here. The energy value up to which all the energy states are completely filled by electrons at absolute 0 temperature, and above which all the energy states are completely empty, is known as Fermi energy. So I will once again explain the concept of Fermi energy. So at absolute 0 temperature, all the electrons will try to occupy the lowest energy state, but the Pauli's exclusion principle the electrons prevents many electrons to together occupy in a particular state. So only one electron can exist in one state. So the electrons will be forced to occupy the higher energy states. So, so if we fill up the energy state from the lowest energy state to higher energy states in such a way that one electron will exist in one state, then the highest state to be filled is called Fermi energy. And Fermi energy is denoted as EF. Now, the occupation index or energy distribution, which we explained in the last class, F of E is defined as N of E by G of E. So we know that N of E is the number of electrons having energy E, and G of E is the number of energy states having energy E. So N of E divided by G of E gives uh, the occupation index, uh, the average number of electrons occupied in the energy states at a particular energy E. So that is called occupation index. So when for E is greater than EF, that means at absolute zero temperature, when energy is greater than EF, so that means energy is greater than Fermi energy. We just now mentioned that the energy states will be empty. So N of E will be 0 when E is greater than EF. So we will get F of E is equal to 0. So the occupation index will be 0 when E is greater than the Fermi energy. Similarly, when E is less than or equal to the Fermi energy, we now understood that all the energy states lower than the Fermi energy are filled. So the occupation index F of E will be 1 for E is less than EF at absolute zero temperature. So F of E will be 0 when E is greater than EF, and F of E will be 1 when E is less than or equal to EF. Let us now substitute alpha is equal to EF by KT. That means uh, for our expression for Fermi-Dirac distribution, that is this expression. Here, one constant alpha is there. This is Fermi-Dirac distribution, and we now substitute alpha is equal to minus EF by KT. Then the expression for F of E. F of E is nothing but N of E by G of E. F of E is N of E by G of E. And the expression for N of E is given here. So divide it with G of E. Then we will get 1 by this one. So alpha is substituted with minus EF by KT. Now we will get this expression 1 by E minus EF by KT plus 1. And I will explain why we substituted alpha is equal to minus EF by KT. In this expression, for E is less than EF and T is equal to 0 Kelvin. Suppose T is equal to 0 Kelvin and E is equal to less than EF. Since E is less than EF, this is a negative quantity and T is equal to 0. So this whole together becomes minus infinity. So this expression becomes 1 by E raised to minus infinity plus 1. So we know that E to the power of minus infinity will be 0. So we will get F of E is equal to 1. So now you understand that when we substitute alpha is equal to minus EF by KT to the expression of F of E, we will get the correct expression for the occupation index when E is less than the Fermi energy. And now consider E is greater than EF at T is equal to 0 Kelvin. So at T is equal to 0 Kelvin and E is greater than EF. So this quantity become positive and T is 0. Now it become E to the power of infinity plus 1. So we know that E to the power of infinity is infinity. So 1 by infinity. 1 by infinity is 0. So we get F of E is equal to 0. So just in the previous slide, we studied that F of E should be 0 when E is greater than EF. And F of E should be 1 when E is less than or equal to EF, as per the definition of Fermi energy. And we also understood that when we substitute alpha is equal to minus EF by KT in the expression of Fermi-Dirac distribution, the F of E gives the correct values, or the occupation index gives the correct values. So we shall conclude that alpha is equal to minus EF by KT, or this substitution is right. So we shall now substitute this equation 92 the expression for alpha in the expression of NED, which we derived earlier. So by substituting the value of alpha in equation 91, we will get this one. This is 93. So this is the final expression for Fermi-Dirac distribution for free electrons in metals. So this expression gives the number of electrons having energy between E and E plus D in a metal. Number of free electrons. So here EF is the Fermi energy. Now we understood the definition of Fermi energy. As per the definition of Fermi energy, at absolute zero temperature, when T is equal to 0 Kelvin, the electrons will be filled up from the lowest energy state to upward in such a way that each energy state is occupied with one electron. So at absolute zero temperature, the highest energy state thus filled is called the Fermi energy. So from this figure, you can see this curve shows T is equal to 0 Kelvin. And this is occupation index. So when E is less than EF, when E is less than EF, the occupation index is 1 for T is equal to 0 Kelvin. And when E is greater than EF, the occupation index will be 0 for T is equal to 0 Kelvin. Now we will see what happens if T is greater than 0 Kelvin. That means the temperature of the metal is increased from 0 Kelvin. Now substituting the expression of F of E, the expression of F of E is this one. So here T is greater than 0 Kelvin and we substitute E is equal to EF. So when E is equal to EF, this quantity becomes 0. So 1 by e to the power of 0 plus 1. So we know that e to the power of 0 is 1. So 1 by 1 plus 1, so half. So F of E becomes half. So thus the Fermi energy EF at T is equal to 0 Kelvin is that energy level in which 50% of the quantum states are occupied and 50% are empty. So from this we can understand that when T is greater than 0 Kelvin at Fermi energy, half of the energy states will be occupied and half of the energy states will not be occupied. So when we increase the temperature from 0 Kelvin, some electrons which are near to EF, near to the states of Fermi energy, will be jumped to higher energy state. And that is shown in this figure. So here this curve shows T is greater than 0 Kelvin. So the occupation index is not 1 near Fermi energy. And at Fermi energy, the occupation index will be 0.5, exactly half, as we obtained from this equation. And for energy greater than Fermi energy, also the occupation index is not 0. So this is a description of Fermi energy. Now we shall derive an expression for Fermi energy. So the total number of electrons in the electron gas having energy between E and E plus D can be written using equation 89 and 92. So equation 89 is nothing but our Fermi-Dirac distribution. This is equation 89. And in this 89 for alpha, we substituted equation 92. Then we will get this expression. This expression. This is the expression for NED. From the above figure, it is clear that at T is equal to 0 Kelvin and the energy E is less than EF, all the single particle states are filled up. That means at T is equal to 0 Kelvin, we know that the occupation index is 1 for E is less than EF. So we can say that all the energy states are filled up with 1 electron. Thus, in this case, NED can be written as GD divided by T is equal to 0 and E is less than EF. So this becomes e to the power of minus infinity. E to the power of minus infinity is 0. So here NED is equal to GED. And this is a very reasonable result because we just now said that for E is less than EF, all the energy states are filled up with 1 electron. So NED will be equal to GED. Number of electrons will be equal to number of energy states because each energy state is occupied with a single electron. So the total number of electrons is equal to the total number of single particle energy states when E is less than EF and T is equal to 0 Kelvin. So the total number of electrons N is given as integrating 0 to EF NED. So we know that when E is greater than EF, NED will be 0. So at absolute 0 temperature, the total number of electrons can be obtained from this integration. And since NED is equal to GED, we shall write this equation, integral 0 to EF GED. So the expression for G of D is given in equation 90 and the derivation is given in the lecture notes, the appendix of the lecture note. Substituting 90 in 96, we will get this expression. So for GD, we substituted equation 90. Equation 90 is this one. This is the expression for GED. So this expression is substituted here. So we shall simplify this like this. The constants are taken outside the integral. And performing this integral, this is a simple integral. And performing this integration, we will get this expression. So this is the number of electrons, total number of electrons in the metal at a T is equal to 0 Kelvin is given by this expression. And from this expression, we shall get the expression of EF, the Fermi energy, simply using simple mathematical steps. So this can be written like this by cross multiplication. Then simplify this expression. Then we will get the equation for Fermi energy. So this is an important equation. And this is the expression for Fermi energy of electrons in the metal. Now consider a problem. If the Fermi energy for the metallic silver is 5.5 electron volt, calculate the number of free electrons per unit volume of the metallic silver. So the Fermi energy is given by 5.5 electron volt. So for doing the calculation, we need to convert it into joules. So multiply with 1.6 into 10 raised to minus 19 to convert it into joules. Then this is the mass of the electron and this is Planck's constant. From the expression of Fermi energy, this is the expression of Fermi energy. So in the question, it is asked to calculate number of free electrons per unit volume. Number of free electrons per unit volume. So the expression can be obtained from 98 divided with V, N by V. So this is the expression for N by V and substitute the values. Then we will get this one. And doing the calculation, we will get the answer. Now we will just study the comparison of three statistics. So we studied three types of statistics. First, the Bose-Einstein statistics and Fermi-Dirac statistics. This too comes under the category of quantum statistics. And before that, we studied Maxwell-Boltzmann statistics, which shall be applied for classical particles. So this one, Ni is equal to Gi by e raised to alpha plus beta Ei minus 1. This is Bose-Einstein distribution. And this one, Gi by e raised to alpha plus beta Ei plus 1 is Fermi-Dirac distribution. And this one is Maxwell-Boltzmann distribution. Now, we shall rewrite these equations like this. Gi by Ni plus 1 is equal to e raised to alpha plus beta Ei. So in this way, these three equations can be rewritten. Now you look at these three equations. And from these three equations, it is very clear that if Gi by Ni is very, very large compared to 1, if Gi by Ni is very, very large compared to 1, we can say that the Bose-Einstein statistics and Fermi-Dirac statistics approximates Maxwell-Boltzmann statistics. So if Gi by Ni is very, very large compared to 1, we can neglect this 1. Then this all three equations become identical. So that is the limiting case in which the quantum statistics and classical statistics are same. That is Gi by Ni is very, very large compared to 1. That means Gi is very large compared to Ni. So for the electron, if there are many states available for the electrons, then Gi by Ni become very large. In that case, we can remove or we can approximate all this equation is equal to Gi by Ni. Under certain conditions, the Bose-Einstein and Fermi-Dirac statistics give results which are virtually identical with those given by Maxwell-Boltzmann statistics. This will happen if Gi by Ni is very large in comparison with the unity. So when Gi by Ni is very large compared to 1, we shall write like this. It follows that for almost all conditions under which normal gases exist, the classical distribution law should adequately describe their actual behavior. There are only very limited number of cases in which the classical distribution becomes not applicable. The temperature is too low or pressure is too high. In these situations, that is when the temperature is too low or pressure is too high, we should apply the quantum statistics, because in that cases, Gi by Ni become comparable to 1. And in all the other cases, we shall consider Gi by Ni is very large compared to 1, and we shall apply classical statistics. So today's class, we studied the application of Fermi-Dirac distribution for the free electrons in metals, and we also studied about Fermi energy, an important concept, and we also studied a comparison of three statistics. Thank you.